welcome back, everyone. For the first talk in the afternoon, we are very happy to have Federico Bonetti from Durham University that is going to talk about symmetry TFTs from Branes.
Great. Thank you very much. Thanks to Giulio and Alessandro for having me at this great workshop. And indeed, today I would like to tell you something about general features of generalized global symmetries and string theory based on an earlier paper in collaboration with Fabio, Ibu, and Sakura, and a paper that appeared today with Fabio, Dawi, and Sakura. So in a sense, if we consider the topic of this talk from far away, it's all about the interplay of two research areas that have been very fruitful in the past few years. And on the one hand, we have this idea that we can study quantum field theories using an approach based on string theory, M theory, brane constructions, holography. And on the other hand, independently from that, we can also ask what is the most general structure of global symmetries of quantum systems and quantum field theory. And though these two topics are logically independent, they exhibit a very rich and fruitful interplay. And in this spirit, in a sense, the message that I would like to convey today is a simple but potentially deep connection between these two sides that involves two actors, one for each side. On the stringy side, we have branes. Of course, they are fundamental both in the context of geometric engineering and as well as in holography. And on the other side, we have the so-called symmetry topological field theory, or the SYM-TFT, which in recent years has really emerged as a key and very useful concept in the world of generalized global symmetries. So to start, I would like to give some motivation, some remarks, and I will start in turn briefly with the first side and then move on to the second. Probably I don't have to say a lot of words to motivate this audience that it's quite a good idea to look at quantum field theories using string theory for various reasons. For instance, using stringy tools, we can access regimes that would be quite hard to study otherwise. For instance, strong coupling regimes in holography. But in a sense, even more interestingly, string theory has really shaped our understanding of the space of quantum field theories. What sort of theories exist, what theories don't exist, including potentially surprising ones, like fixed points of the RG flow in 5D and in 6D that are intrinsically strongly coupled, and also exhibit a rich zoo of dimensional reductions that trickles down in 5D, 4D, 3D, and so on and so forth. So all this would be, sometimes it's quite hard to study purely with field theoretical methods. And another sort of personal motivation is that even if we already know something on the field theory side, sometimes finding its counterpart in string theory is nonetheless extremely useful, because it can shed a new light that makes some very non-trivial statements on the QFT side a bit more apparent on the stringy side. And here I'm borrowing a classic example of, say, S-duality of n equals 4 that becomes geometrized when we think of this theory as coming from a reduction on a T2. And so given that there are strong motivations to study QFTs in string theory, let's now switch to the other side of the first diagram in the first slide, namely, why should we care about generalized global symmetries? Well, in a sense, just because we know from past experience in the subject that symmetries, global symmetries, are extremely powerful. We know that they can organize the spectra of operators on our theory. Sometimes they exhibit anomalies. If they do, those have to match, for instance, along RG flow, the 't Hooft anomaly matching argument. It's, of course, also extremely useful to think about spontaneous breaking of a symmetry. Sometimes it leads to Goldstone modes. And we can also study phases by asking ourselves in sort of like, in which vacuum is which symmetry broken, in which one it's not. So all these are old ideas. What's new in the field since the seminal paper of 2014 is that has been a realization that all these very useful concepts that we know from ordinary symmetries can be vastly generalized. And the key idea is to think of symmetries as topological operators. And in order to essentially give a short motivation and mostly fix my notation, because probably the audience is already quite familiar with all these concepts, let's trace back a very basic example as a quick warm-up. Let's consider an ordinary U1 global symmetry in your favorite QFT, let's say in 4 dimensions. We know it admits a Noether current, which is conserved. And if we want, we can repackage it into a closed 3 form. That's just notational convenience. If we do so, we can integrate it on our favorite 3 cycle. It could be a spatial slice. That's what's usually done in textbooks, but it could be also something else. For instance, in a weak-rotated theory, it could be literally anything. And conservation of the current becomes closure of J3, and therefore the statement that if we define this operator exponentiating the integral of the current, the operator will not change if we modify its support slightly. And the idea is actually quite simple in its elegance. It's somehow forget the current and focus on the topological operator labeled by some group element. If we do so, first of all, we can describe continuous or discrete on a very democratic footing. And more dramatically, now we can play with dimensions and codimensions in a relatively straightforward way. So we can go from, say, an ordinary or zero-form symmetry. It acts naturally on local operators, surrounding them with a codimension 1 sphere. Or, for instance, we could consider line operators, so that now the codimension of the topological operator changes. In 4 dimension, it's this surface, D2, but it acts in a very similar way by surrounding it, by linking, if you wish, and then shrinking, and it's going to act on our line. So this is how we go from ordinary symmetries to higher form symmetry, but we can do much more. We can do, for instance, higher groups. In a nutshell, those are non-trivial mixtures of higher forms of different degrees. This is a bit of a crude characterization. Of course, one can define them a bit more properly, but just for the sake of illustration, there's one example that I'd like to remind you for the rest of the talk. It's a simple example of a possible 2 group, which is a mixture of 0 form and 1 form. In this specific class of examples, what happens, like why are the 2 symmetries intertwined? What happens is that if one of the symmetry generators of the 1 form symmetry, so the surface, the D2 guy, it pierces through one of the 0 form generators, it reappears, but with a different group label. It's like H going to G acting on, H acting on by G. So we will see later on that this example appears naturally in some stringy constructions, and we will have a way of thinking about that in a more stringy way. But so far, everything was still kind of very much group-like. Maybe groups at different form degrees talking to one another in interesting ways. However, there are much wilder generalizations available that go under the umbrella term of non-invertible or categorical symmetries. And one way to characterize what's going on in these further generalizations is to think about the fusion of these topological operators. Since they are topological, we don't have to worry about short distance singularities in taking their OPE, quote unquote. And in the more standard case, either ordinary symmetry or higher form, the fusion is group-like. But this can be relaxed to a more general fusion algebra, so that we don't have only one object on the right-hand side, but rather a sum of objects with some coefficients. And as a result, some of the simple objects that we start with might fail to have a multiplicative inverse. So that's the name, hence the name non-invertible. And they're also called categorical because it turns out that this fusion data is part of a larger mathematical data, and the picture that has emerged is that the best way to think about symmetries in general is in terms of higher category. I will not need to dwell further on this notion for the rest of the talk, but I thought it was important to mention. And actually, like, are these symmetries really new? In a sense, in 2 dimensions, to some extent in 3 dimensions, they have been known for a long time. They, in a sense, reflect also how the structure of OPE works into the TFT. The real surprise that has been found in the last 2 years, approximately, is that they're actually ubiquitous in higher dimensions as well. And you don't have to look for some exotic QFT to find them. you can consider pure Yang-Mills theory with an appropriate gauge group, and they're going to be there naturally. Even something, if you wish, even less exotic, like QED, or some suitable massless limits of QCD. So something that is very much intimately related to the standard model. And as you can see, there has been a lot of work recently on the subject, but in a sense, I think it's fair to say that we're just starting to scratch the surface of the dynamical implications of these novel kind of symmetries. One of the earliest applications has been a rethinking of the pion Lagrangian, for instance, in terms of one of these non-invertible symmetries. And there's also ongoing work on applying them, for instance, to problems related to neutrino masses and their natural hierarchies beyond the standard model physics. So I believe this really gives strong motivation to explore these sort of structures. And so having introduced, as you can see, we have gone from like ordinary symmetries, higher form, higher groups, non-invertibles. There is a whole zoo out there. And I would like to describe one operation that sometimes helps us navigate this zoo of options, and that's the gauging of a discrete symmetry. We are probably very familiar with the notion of gauging an ordinary symmetry, but in a sense, that's an operation that involves introducing a connection and path integrating over the connection and all of that. In the discrete world, it's actually quite simpler. As you can see, it looks like a discrete version of a Fourier transform. And if you start with something that has a p-form symmetry, so little b would be the background field for that, you end up with a new theory that has a quantum symmetry of a complementary form degree, and you can always go back. So this is like an invertible operation, just like the Fourier transform. And to give a famous example, if we start with a gauge theory in 4 dimensions that has a gauge group SUN, this has an electric one-form symmetry because of the center. This has already appeared also in Cyril's talk, for instance. If we gauge that electric one-form symmetry, we land on a new gauge theory that has the same gauge algebra, but a different form of the gauge group. It's PSUM, so the quotient by the center. So clearly the center now is gone, but we get it pi 1. So we have now a magnetic one-form symmetry. That would be the quantum symmetry that we find under after gauge. But we can go back, gauging the magnetic one, going back to the start. And so this example is a little boring because the two sides are relatively similar. But in other examples, performing a discrete gauging can bring you from an ordinary symmetry to something else, higher groups, or even non-invertibles. And I just would like to flush one example that I find sort of like illustrative of the richness of this sort of constructions. So here is a little web of some of the global variants of gauge theory based on SO4N algebra. No supersymmetry, pure Yang-Mills. And there is a whole zoo. You can consider the SO theory, the spin, PO, pin plus. You can pick your favorite global variant. And as you can see, some exhibit anomalies, some have a true group, and the guys on the right have these more exotic, or well, not so exotic at this stage, non-invertibles. And we can move from one to another through various gauging procedures. So in a sense, this begs the question, is there a simpler way to think about what is happening? Do we really have to keep track of these complicated webs of interactions and different kinds of generalized global symmetries? Can we package information more efficiently? And the answer is affirmative, and it's provided by the symmetry field theory, the SIM TFT. So the idea is that this is a gadget that lives in one dimension higher with respect to the theory you want to study. So for a gauge theory in 4 dimensions, this is a topological theory in 5 dimensions. And it knows, or like it can encode, all known generalized global symmetries, essentially. So, of course, the ordinary ones, the p-form ones, p groups, we'll see that it takes into account the discrete gauging operation in a very efficient way. It can know about non-invertibles. It definitely knows about anomalies and much more. So this introduction was to try to motivate why. So on the one hand, that there is a rich, extremely rich structure of generalized global symmetries, and on the other hand, that we need an organizing principle in order to motivate the SIM TFT. That was like one of the main ingredients from the very first slide. So having gone through an introduction, hopefully motivating a bit the rest, oh, that's a typo. Well, we'll see that I want to discuss a little closer the sim TFT, and then I'll switch gears to the stringy side of the story. And after some general considerations, I will turn to some more specific application if time permits. Okay, so if there are no questions, I would like to say something more about the SymTFT. What is it exactly? How does it work? And how is actually able to connect all these various aspects that I've shown on the previous slide. So at the basic tenet of the SymTFT idea is the so-called sandwich construction, advocated by Fried and then Fried, Telemann, Moore. So what do we have and what do we want to do? We want to study a physical system. It's a QFT-T that has some global symmetry S. This could be a group, could be a higher group, it could be a higher fusion category. And our goal is to separate the abstract aspects of this symmetry from the dynamics of the physical theory. This is inspired by what we know to be very useful in general in math and in physics. It's useful to have a notion of an abstract group and then ask ourselves what happens when that acts on our favorite physical system. And the tool that achieves this is the SymTFT. And in a sense, the separation of these elements is literally a separation in space-time. That's why we open up an auxiliary dimension. We go one dimension higher with this extra interval, because in this way we can have two separate boundaries of this auxiliary system. On the one hand, the yellow guy, the B-sim boundary, that's always a gapped topological boundary. So this is topological in nature, and loosely speaking, that's where the abstract symmetry lives. On the other hand, we have the physical boundary. This is where our dynamics takes place. This, generally speaking, it's not gapped. It could be, if we want to study, say, a TQFT in the first place. And as I mentioned, the idea is that we are opening up this sandwich to separate aspects of generalized symmetries and how they act on physical systems. But at the end of the day, we want to recover the actual theory we want to study. To this end, we have to squeeze everything back, go back to our original space-time dimension. And we can do it freely because the bulk is topological. Clearly, the length of the interval has no physical significance. So let's have a look at a simple example. Let's consider as our theory, let's consider for the n equals 4 super Young-Mills, and let's choose the gauge group SUM so that we know that there is an electric one from symmetry. So let's focus on that as our symmetry. How do we encode it in this 5-dimensional auxiliary way? Through a very simple topological field theory, simple yet rich, with this action, the so-called BF theory, with two-form fields and one derivative. And in this case, on the topological side, the B-sim boundary, we choose Dirichlet boundary conditions for B2 and free boundary conditions for the other. And on the physical side, that's where the local degrees of freedom of the gauge theory live. That's something that also has appeared in Cyril's talk. It's sometimes referred to as the relative theory because it lives at the boundary of the SymTFT. And we can denote it with the Lie algebra as opposed to the group as a reminder that it only knows about local degrees of freedom, or like it's where the local degrees of freedom are encoded. And this is a 5D TQFT in its own right. It has some topological operators, and some of them are quite simple to write down. We just take the holonomies of these B2 and C2 fields, and those are well-defined gauge invariant operators. And as you can see, essentially each of them is a Z2, and that also checks out with something that has appeared in Cyril's talk, namely the idea of this defect group, which is Z2 times Z2, because we know that here we're looking at the electric theory, but there is also a magnetic theory, and the SymTFT should know about both. So here, by 2, sorry, ZM times ZM. It's a typo, thank you. And indeed, the discrete gauging, it's very natural to perform in this context. We keep the same topological bulk. We keep the same B-phase boundary condition. And all we do is changing the gapped topological side. Essentially, in this simple example here, we exchange the roles of C2 and B2. And that's the same as performing this discrete gauging that I mentioned earlier. But of course, now as you can see, we are rephrasing the problem of considering possible discrete gaugings and to a problem of classifying topological boundary conditions for the SIM-TFT. And in this instance, it has been shown that there is a precise correspondence between this set of boundary conditions of the 5D BF theory and exactly the various global forms of the gauge theory in the spirit of the reading between the lines paper. So that's the first promise, like the SIM-TFT can take into account discrete gaugings very efficiently. You keep everything fixed, and if you can, you change the topological side. But let's see what more we can do. Well, that was a simple example, but nothing prevents us from considering some generalizations. What I wrote here is a relatively simple one. It's more BF terms with forms of various degrees, but I'm also allowing for a possibility of other terms that are monomials in the B fields, for instance. And here I'm using a continuum formulation. Everything is continuous fields, but if you look at what happens on shell, you'll see that they're all flat and that their holonomies are discrete. So it's a way of encoding discrete symmetries. And these extra couplings, we can think of them as anomalies once we choose a global form. So once we choose the boundary conditions on the topological side, if we close the sandwich, these curly A will tell us something about the anomalies of the absolute theory. And as a TQFT in its own right, the SIM-TFT has itself topological operators. Well, only topological, clearly. And in the simple case where the anomaly term is not there, just like in the previous examples, they are holonomies of these various B and B hat fields that we have. Do they do anything interesting? Well, at the very least, they form pairs that link non-trivially. That's exactly what the BF coupling is telling us. And so for each B, it has a BF partner B hat, and their space-time dimensions work well together, so that if you take a correlation function of two of these guys linked, literally linked, so their total dimension is 1 unit lower than space-time, you'll have a non-trivial correlator, or if you wish, a non-trivial commutation relation. So this is like at the core of a simpler example of a SIM-TFT. But the general philosophy is that it is a TFT in its own right. It has topological operators, and those can have non-trivial correlators. Why do we care? Well, because now, using the operators of the SIM-TFT, we can get both objects of interest. On the one hand, we have the symmetries. On the other hand, we have what the symmetries are acting on, so the charges. Let's start with the symmetries. So in the world of the SIM-TFT, in the sandwich construction, as I mentioned, we really want to try and separate the kinematics of symmetries from the dynamics of the physical system as much as possible. So in this spirit, the best thing to do is to think of the topological operators that implement a symmetry as living on the topological side of the sandwich. So in these pictures, I'm only depicting half of the sandwich. That's sometimes called the quiche, or like an open-end sandwich. I'm omitting the physical system because I'm trying to think about an abstract symmetry that can act on several different things. A simple thing we can do is take a topological operator in the bulk and literally project it onto the topological boundary. And in fact, for SIM-TFTs that describe abelian discrete symmetries, that's all we can do. We don't lose anything if we do this. For the n equals 4 example, we have chosen the Dirichlet boundary conditions for B2, so the other guy, C2, can be brought parallel, and there it becomes a generator of the one-form symmetry. So that's one side of the coin, the symmetry. And then it acts on the charges, or generalized charges, if you wish. That's terminology. We say that something is a Q charge. It simply means that it's some operator of dimension Q, space-time extended in Q directions, that transforms under some global symmetry. How do we realize it in the sandwich? Well, the main actor is again one of the Q topological operators of the SIM-TFT, but this time, as you can see, it runs along the interval direction, and it hits the physical boundary. So that's why the resulting object O does not have to be topological, because things that live on the SIM side, on the physical side, don't have to be. And in our favorite n equals 4 example, these are holonomies of B2. They can pierce the physical boundary, and where they touch it, that's where we have a Wilson line. That is the object that is charged under the one-form symmetry. And now we can make use of the linking that we have in 5 dimensions to describe the action of the symmetry on the charge. In fact, you can see it probably already from the picture. It's quite intuitive. These two guys are linking in 5D, and if I smash the interval, it looks like something surrounding the Wilson line. So we see the two actors playing their respective roles, and in a sense, at this stage, it might look a little bit like an overkill because this is quite simple, but it's very useful to think about it in these terms, because what we have been learning in the last year is that actually, like we always say that p-form symmetries act on p-dimensional operators, and that's correct, but they can do much more, to the point that they can act on operators of various dimensions, and it turns out that q-dimensional operators, so q charges, are best thought of as a higher category, q plus 1 rep of some group. If you have groups, if you have something more abstract, it's going to be even more abstract. I'm not going to go this way, but I wanted to mention it because it provides motivation to think about in these more abstract terms about something that is in this instance looks quite simple, but there are cases where there is something richer going on. Okay. So what was the bottom line, essentially? I would like to emphasize that the SymTFT has topological operators on its own. They link non-trivially, and depending on how you put them, they can play both roles, the symmetry and the charge. I mentioned that one can do more than just simple linking, and there is indeed one specific example I'd like to show. It's an example in which, as you can see from the picture, our topological object, D, it's already projected, moves, and as it moves, it touches the other Q guy that runs along the interval direction, and something else gets created in the process. And as you can see, once everything gets projected, the same sort of creation of a new topological operator happens in the absolute theory. So this means that this D operator is taking something that was a genuine operator, OQ, and it's turning it into something non-genuine. Non-genuine in the sense that now it lives at the end of a topological line or topological surface. Now, this might seem completely maybe ad hoc, but it actually happens in many examples. It happens in the Kramers-Poirnier duality already in the C2D Ising model. And in 4 dimensions, it actually happens in relatively innocent-looking theories like QED itself or n=1 super Yang-Mills. So you don't have to look hard to find instances. Here I should say PSUM to be precise. It's in the magnetic theory.
This looks pretty much like the analogy we can expect in the
Precisely. Absolutely. So you're jumping ahead, and indeed we will see that the Hanani-Witten ray moves in string theory precisely capture this sort of generalized charges. So indeed, you're absolutely right. Okay. And there is one more ingredient I'd like to mention in this world of the SymTFT. So essentially, my idea was I would like to guide you through some of the interesting ingredients of the SymTFT in abstract, and then see how they will pop up quite naturally on the stringy side. So the ingredient I would like to mention now, it's the so-called condensation completion. We can ask ourselves, what are all the topological operators of the SymTFT? And in general, it's a hard question. And there are some maybe counterintuitive aspects to this. Even in simple examples like BF theories or something like that, one should include something called a condensation defect. In loosely speaking, it's a mesh of lower dimensional operators inside a bigger one. And the bigger one can also be just the identity operator. So in the picture, I'm depicting a mesh of surfaces that, for instance, implement a one-form symmetry inside the 3-dimensional identity defect. And it turns out that these objects are very important, on the one hand, for the mathematical consistency on how we think about symmetries in terms of categories. That's related to the so-called Karoubi completion. And in practice, also because in many examples where you have a non-invertible symmetry, after you do fusion of the non-invertible generators, you naturally find these condensations. So it would be inconsistent not to include them in the spectrum of topological operators. And therefore, we should keep in mind that they are there and keep them in our sort of wish list of things we would like to see on the stringy side. Okay, so that was a sort of quick overview of some aspects of the SIM-TFT, and now we will see that indeed in string theory, in quite broadly understood, so both in terms of geometric engineering but also holography or Branes, we will see the appearance of those features. So let's start with a very sort of a general picture from afar. For definiteness, let me start with geometric engineering. So we have seen already in a few talks in this workshop that the key idea is to take your favorite string theory or M theory and consider it on a space-time which is the product of Minkowski in the dimension you would like to study, and an internal space which is non-compact so that we don't have dynamical gravity and we're studying a QFT, and usually also singular, so that it supports some sort of localized degree of freedom that are responsible for engineering a QFT that is non-trivial. In that sense, if we look at the cone picture where we have this non-compact internal space X and the base of the cone I'm calling L for link, there is an intuitive notion that the physically interesting dynamical degrees of freedom are located at the tip of the cone. That's where the singularity sits. We could imagine maybe resolving the singularity, wrapping Branes, getting BPS states. So that's where the physical side is. So in that sense, it's natural, if we want to compare the geometry to the SIM-TFT picture, to associate the R equal to 0, the tip, to the physical side of the sandwich, where the dynamics and the physics is happening. In that sense, therefore, we are led to think about the other side of the sandwich as living at infinity. And that also checks out with another piece of information about these geometric engineering constructions, and namely that in order to fully specify our string construction, we have to choose some fluxes at infinity. That essentially stems from the fact that due to flux non-commutativity, when we have torsion, and in many examples this L geometry has torsional cycles, the fluxes are not all commuting, and therefore you cannot just simply set them all to 0. Just like, of course, we cannot set, I don't know, all the x and the p coordinates simultaneously to our favorite value. Therefore, we have to make a choice. And that choice is naturally mapped to the choice of a gapped boundary condition on the topological side of the sandwich. So in a sense, we can see there is a quite direct and satisfying correspondence. Now, in the SIM-TFT world, the interval direction is topological. Of course, in string theory, it's not. Like, there is a whole extra dimension that opens up. So we could say, in a sense, if you wish, that in string theory, it is gravity or quantum gravity that mediates between the two sides of the sandwich. Whereas in a purely field theoretical context, the sandwich is topological and we can just perform the interval compactification. Yes?
In what sense is quantum gravity that mediates?
Well, just in the sense that there is, that it's not topological.
Well, we think, no? So the gravitational coupling is zero. Also the link has infinite volume.
Yeah, that's right. It's a limit in which
And dimensional gravity.
It's dimensional gravity.
And dimensional strength. There is everything, right? But you're looking at the very low energy number.
So it's
yeah, absolutely.
the gravitational modes, there are no topological transitions, there are no quantum gravitational effects.
I think when you look at very low energy,
It is a 4D gravity.
Yeah, that's right. No, definitely.
Yeah, but it's not, there is not an intrinsic quantum gravitational. No, if you have charges which are carried by topological operators, and you allow for topological transitions, which is a signature of hardware of quantum gravity.
No, it's quite simple. It's more like to contrast that. So in the world of the SIM-TFT, everything is strictly topological, whereas that's not the case in the full string theory. So this was to give a picture of like what is, since we cannot just shrink the geometry as we wish, because there are equations of motion that have to be satisfied. This was an idea of trying to think in a different way of how these two sides of the sandwich talk to each other.
So what you mean is that like the choice of boundary conditions for which you specify the background, that's part of gravity.
It's part of gravity, yes. Yeah, it's part of space-time in the higher dimension. And right, thanks. And I'd like now to use this picture to essentially try to make contact to also other concepts that have already appeared in this workshop a couple of times. So hopefully that helps to chart a little bit what's happening. Thinking about, if you wish, three types of branes we can consider in these setups. So we have branes that, for instance, wrap resolution cycles at the singularity. So those are states that have a finite mass or a finite tension. The BPS spectrum has appeared in many talks in the workshop. And intuitively, it's clear that they belong to the physical side of the story. They are dynamical excitation of our theory. Then we have branes that extend along the radial direction and go all the way to infinity along some cycle in Ln. And again, intuitively, it's clear that these now correspond to operators that will extend along the interval direction in the sandwich picture, and they're going to go from the physical side to the symmetry side. They have infinite tension, there are defects, and indeed, that's the key idea of the defect group that has been applied to a variety of geometric engineering constructions. And as you can see, so in a sense, those were the branes that were known for the longest time. But now that we have this picture, it's natural to consider a third kind of branes. Namely, what if they live at a fixed value of the radius, so they don't connect the two sides, but they live on the symmetry side, so they live at infinity. So we're going to think about branes that wrap some cycle at infinity, and since they're infinitely far away from the physical degrees of freedom, they are effectively topological. So that's the key idea, that branes at infinity are identified with symmetry generators. And
what do you mean by effectively topological?
I will comment on that more. Thank you. And so here I was discussing geometric engineering, but actually we can repeat the same logic for holography. We can consider a probe picture first. Then we just have literally a bunch of branes that live at the tip of a cone. Maybe the cone is flat space, a cone over a sphere. If we think of a back reaction and a near horizon limit, clearly then we will see the emergence of an ADS or maybe near ADS geometry. But the same philosophy applies. So the physical degrees of freedom will live at r equal to 0, which in this coordinates is like the origin of ADS, if you wish. So the bulk, whereas the topological side lives at the conformal boundary. So this also fits with the intuition that it is the bulk of the gravitational system that it's dual to the CFT, say we want to study. And from that point of view, once again, we're led to thinking, let's put some branes at infinity. Here, infinity means the conformal boundary, and let's realize symmetry generators that way. So that was the original proposal from last year, and that it has been applied to geometric engineering and many other situations. And now also to go back to Cyril's question, what does it mean to put branes at infinity? Well, the idea is that we should consider a suitable topological limit. Of course, the branes themselves are far from being topological. They support all sorts of excitations. So we should, we want to freeze all of that away. And the main idea is that we should be focusing on something that lives in a region at large R. We don't want to touch the dynamical degrees of freedom at small r. We're living at large R. So in the large radius limit, we can adopt, for instance, a classic argument by Witten about derivative counting to argue that the BF terms, for instance, dominate, or in general, topological terms dominate in the supergravity action. But actually, we can use the same argument also for the word volume theory of the brane itself. In general, it consists of both dBi terms as well as Wess-Zumino topological couplings. But from this point of view, the brane at some location R has a very large effective tension. And that ends up freezing, or if you wish, decoupling all the non-topological excitations of the dBi action. And ultimately, we're only left with the Wess-Zumino couplings. So both in the bulk, supergravity or M theory, whatever, and on the branes, we should focus on topological terms. And in a sense, we can think of it as a truncation, because what we want to describe are something that on shell is a flat field with discrete holonomies. But if it's flat, it's not going to source, for instance, the metric or the dilaton in an interesting way. So that's ultimately why what we want to focus on is a specific topological limit, or topological truncation, if you wish, where we capture just the elements that we need in order to perform the analysis.
Why can I put the brane at infinity without it falling back? It looks like it will want to minimize extension and go back to the
it would. Like, we can think about it either as a limiting procedure. Once it's at infinity, it's just completely non-dynamical, so it doesn't really want to go anywhere because it doesn't participate in the dynamics anymore. Or we can think about it almost the other way around. Like, we can imagine from it starting at infinity as sort of boundary conditions, say in holography. And then, if indeed that's true, if we were to give it a little tilt and put it an epsilon into the bulk, then it would become dynamical and it would start to fall. So that's true. Like, it's not a dynamical process that brings the brane all the way to infinity. It's more like once it's at infinity, it decouples. It doesn't participate in the dynamics, and it can stay there. Yes.
Especially for higher possibilities, often some topological operator can stop to be topological if the theory has additional like charge matter, which can screen charged objects. And in this setup, this can arise, for example, if you have compact cycles on which you can wrap branes, and you have extra matter which screens the charged object. So I could imagine a situation in which you are wrapping a brane at infinity. This is topological. I mean, you're saying it's topological because it's at infinity, but then the geometry is such that you can also hook up extra matter charge screening the symmetry. So how is it possible that the brane at infinity knows whether there are or not extra cycles which allow you to use extra matter?
I would say that, in my understanding, the screening mechanism applies to the ones that stretch along the radial direction, because we want to screen indeed non-topological operators. So I'm not aware of a screening process that applies. So in other words, we screen charges. I'm not aware of a process in which we screen symmetry generators.
For example, it might be that you have to resolve the singularity, so you have extra compact cycles.
Right? No, that would indeed be the case. Maybe here I was a bit too quick. Indeed, as you pointed out, in the second point, we should really think of a quotient of things that are non-compact up to compact ones, precisely because of screen. But that's not the case for the branes at infinity, because they simply care about the topology of the link. In a sense, they're completely agnostic about the filling, in that, like, we can work at the CFT point if we have a CFT. We could consider going to some moduli space branch or consider deformations. And in a sense, that's part of the power of this approach. Being agnostic about the filling also means that we are not relying on any sort of Lagrangian description, if available, or anything of that sort. So to go back to your question, I'm not aware of a phenomenon by which something that lives at infinity gets screened by a compact cycle deep in the interior. Okay. Thank you. And indeed, so everything sort of started. Yes, go ahead.
Back to my question. I'm not quite sure I see where the way is it. Because I was saying that it might have been intention, but that's not necessarily the case, right? Because often I would expect actually wrapping some torsion cycle on
That's true, yes. But as you mentioned, like everything, the size of the boundary itself, it's infinitely rescaled. I think that's true. Okay. So there was this list of aspects of the SIM TFT, and now let's try to recover them from Branes. For reasons of time, I won't discuss everything. I'll just discuss few aspects. But let me tell you first what we can do. We can definitely recover the BF terms. So that's like the backbone of this sort of SIM TFTs. They encode, like to remind you, they encode the fundamental linking process by which the whole process of symmetries measuring charges happens in the first place. They can also encode though anomaly terms. And more interestingly, and related to this newer work, they also encode the condensation completion, that is one of the fundamental ingredients, and this notion of generalized charge. They also encode fusion. I won't discuss fusion in detail today. If you're interested, you can have a look at the older paper and then also other setups. But maybe just quickly to mention that it really fits very nicely with this brane intuition, because we know that deep branes have a localized gauge field that lives on them. And that gauge field, it's not a bulk field. So it's not subject to the same sort of boundary conditions than the bulk fields are. So even in this topological limit, it survives as a topological dressing, if you wish, of the symmetry defect. And those topological dressings are really key, for instance, in the computation of non-invertible fusion rules in many examples, including, for instance, the PSUM super Yang-Mills theory. In my paper from last year, we have studied that in the Klebanov-Strassler setup, and we use branes to argue for the fusion rules. So I wanted to mention this, and I'm happy to discuss if you're interested. But for the rest of the talk, I'll leave fusion aside, and I'll discuss briefly some other aspects. The next couple of slides are maybe a little more technical, but I'll try to be not too specific, like not too much technical. I mentioned that we want to consider a topological limit or a topological truncation. We would like to do that efficiently, and we found that a way of doing so is to modify a little bit our usual description of the bulk supergravity action. So here we perform two tricks. The first trick is to go one dimension higher. So say if you want to study 2B, focus on auxiliary 11-dimensional action. And then, for instance, we see this coupling here, H3 with F3, F5. This is nothing but the usual Chern-Simons of type 2B, just uplifted one dimension higher. But then we can also consider, if you wish, the kinetic terms, or rather a topological counterpart to those, by enlarging the set of fluxes, including not only old electric fluxes, but also all their Hodge duals. So here we have H7, for instance, and all the Fs, not just the lower ones. And as you can see, they are naturally coupled in BF terms, with F5 being self-dual, so it couples to itself. And we can even include sources that we can think of as branes, because those are the magnetic sources for these objects. So this is a purely topological action in 11 dimensions. The actual physical theory is recovered, as you can expect, if we impose the fact that these fluxes are actually dual, so that we don't just double the degrees of freedom. And operationally, this effective action is nice because you can literally vary with respect to F to the field strength itself, not to the potential. So that makes it easier to deal with gauge invariance. And you will get the Bianchi identity for your favorite field, including both the effect of non-trivial Chern-Simons, as well as the effect of sources, like a D-brane, if you have one, for instance. And the philosophy, therefore, would be to start from this higher dimensional theory and do a reduction on the link. So this is in practice how these sort of computations are done. So to give a little orientation, we are interested in studying a physical theory in d dimensions, say 4. We want to compute the sim TFT in d+1. Let's describe it with an auxiliary action that lives in d+2 dimensions. Maybe this is reminiscent of the anomaly polynomial for ordinary symmetries that naturally lives in 2 dimensions higher. So if you start from a gadget like this and you perform the reduction on the link, you will generically land on something that looks like this. So we have lower dimensional BF terms, just inherited from above. And yes, then we can have some polynomial interactions, and we will have sources. Now, these are now wrapped branes, because we're going down. The internal space is gone, so they are wrapped branes. And I'd just like to mention the origin of these BF terms. Clearly, it can be in the original BF terms themselves. So that's related to torsional effects. But it could also come from these cubic couplings, because in the presence of flux, one of the entries of the cubic coupling gets replaced by its background value, say n units of flux for F5 in ADS5 times S5, classic example. So F5 becomes a number, H3 wedge F3 effectively will end up describing a BF coupling if you go through the process. Yes. Yes, in this formulation, that is not apparent, but in a sense that's on purpose because it's something I haven't written down. But one way to deal with the effects of flux non-commutativity is to imagine a sort of a KK reduction onto torsional forms. And that can be done using non-closed forms of suitable kinds. And the flux non-commutativity, morally speaking, it's encoded in the kinetic term. So in a sense, thanks for the question. It's an important caveat. It is true that it's always true that nothing depends on fluxes that are not flat on shell. So in that sense, the usual notion of kinetic term is suppressed. But sometimes, indeed, we have to use, morally speaking, the kinetic terms, or rather their sort of topological counterparts, to take into account the flux non-commutativity effects. And those flux non-commutativity effects are known to survive at extremely long distances. They're not suppressed in a sense. Thanks. Okay. And so briefly, once we have this picture of a bunch of fluxes and their magnetic sources, so the little f's and the little j's, we can do various things. A very natural operation that has already appeared in the CMTFT is the linking operation. In this language, we can write it like this, if we wish, with J, D inverse J. D inverse is a little a formal notation, but geometrically it's very clear what's happening. We're taking the intersection of one of the supports with a surface that bounds the other guy. So morally speaking, that's where the D inverse comes from. So that's a standard definition of a linking number. And here we find it re-expressed in the language of sources, where, as I mentioned, the sources correspond to wrapped branes. But we can do more. We can do triple linkings, and there is a whole bunch of them. And here there is a cute example that I borrowed from this paper here, Puto Wang Yao, of Borromean rings in 3D that don't quite link pairwise, but all together at the same time can have a non-trivial linking. And the importance of this for anomalies was already also emphasized in this paper. And we confirm exactly the same picture using Branes, namely that the basic pairwise link encodes the BF terms that are the backbone of the theory, but we can also consider more complicated linkings, and they encode anomalies. And our results match nicely with both reduction of higher dimensional Chern-Simons terms that many authors have studied and have considered in M theory in terms of reductions with flux, and also without fluxes, but with interesting torsional geometry, and this flux non-commutativity effect that we have considered. well, it's there are some sorts of cubic anomalies. I think, if I'm not mistaken, the ones that don't have a boxed-in map, so like say a BBB, B2, 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 for instance, those would translate in this language to a configuration of this sort. And roughly speaking, if you start removing some of these D inverse operators, that corresponds to introducing boxed-in maps in the anomaly term. Thanks. Okay, good. So there's not a lot of time left. So let me though mention this part because it's one of the new results. Going back to two groups and justifying why I showed you that picture earlier. So can we see two groups or some two groups in string theory and how? And here we focus on one example, namely n equal 4 super Young Mills with gauge group spin for n. So this is one of the various global forms in the zoo that appeared in an earlier slide. Holographically, we're doing ADS5 times RP5, and we know, also based on previous work, what are the symmetries and how are they realized. It's not important to follow all the details. The important point of this slide is to show you, on the one hand, that we identify both what the symmetry operators are for the one from symmetry, as well as what the charges are. And here, this global form is interesting because it has a center that consists of two Z2 factors. And the outer automorphism of the algebra exchanges the spinor and co-spinor representations. So it gives you here something where, if you wish, S goes to C, or equivalently, S goes to itself, but with an extra V that comes out. And in this formulation of the extra V that comes out of the intersection, we can reproduce it from brane physics, because we know what the branes are. This red guy is a D3. As such, it is a source for C4. And if we think about what happens to the D5 as it pierces through, it senses this jump in C4, because there is a coupling on the word volume of the D5 of C4 to B2. So in particular, due to this coupling, a jump in C4 induced by the D3 as we pierce it and we go through, as you can see, induces an F1 charge because of the B2 factor. So that means that an F1 has to be emitted in conjunction to preserve the charge. And in this way, we can reproduce this instance of a two-group relation in the spin for n theory. Good. And now, with this, I can be very brief because, in a sense, the main message of this slide is in the title. Well, on the one hand, we know that we should care about condensation completions. On the other hand, string theory suggests a very natural way to at least get some of the condensation defects. Namely, if we consider a brane and an anti-brane, the top dimensional charge is going to cancel, but there can be some remnants. That's also related to the Tachyon condensation process, by which virtually any lower dimensional brane can be obtained by higher dimensional ones in this way. And we have checked explicitly in a couple of examples that this philosophy can be translated into actual computations that reproduce condensation defects in these two instances. And this is also related to the work of Ibu and his students that also appeared today. And finally, as it was anticipated, clearly Hanani-Witten transitions play an important role in all of this story. Pictorially, it was already kind of clear. This is a very brief reminder on Hanani-Witten. Essentially, in a nutshell, we have a bunch of branes that share some directions, here 0, 1, and 2. And then, as you can see, in the other directions, they link. They fill everything except one slot. If we try to unlink them, a brane is created in that last direction. So that's supposed to be this J1 guy here. And actually, we can see it neatly from this formalism because the current itself is not really closed because of the Chern-Simons term. So as you can see, there is a known conservation. So that's the creation. And it's proportional to one of these JD inverse J objects which encode the linking. So that's how the linking, unlinking translates into brane creation in this magnetic language. In practice, we can use Hanani-Wittens in two ways. The first way was the one that was already anticipated, because as you can see, the pictures are essentially the same, but nothing prevents us from arranging things in a slightly different way. Namely, what if both the first and the second brane are not extended along the radial direction, and we try to link them or unlink them? Now we're going to generate something along R, and something along R is a charge. So that means that we have a mixed anomaly, because there is an ambiguity if we try to resolve radially these branes, or if you wish, we can imagine to sort of project everything, and then we see that the intersection of these two objects is itself charged under one of them. And the fact that the junction of two topological defects is charged under another one, it's a hallmark of 't Hooft anomalies. So that's a new way of thinking about anomalies from Hanani-Witten transitions. And finally, we had some concrete computations based on the Hanani-Witten transition in this example of duality and triality in n equals 4. This is probably more for the experts, so I'll be quick. The main idea is to work in type 2b, where duality and triality becomes the SL2Z gauge symmetry of type 2b string theory. And on the field theory side, we know that we should tune the tau coupling to very special values in order to access points that are fixed under S or ST. And in type 2b, we tune the coupling tau, the XU dilaton, so that we are then free to insert a certain kind of 7 branes, whose monodromies precisely encode the action of the duality or triality symmetry. So this is something that was understood last year. We have used it as a computational tool to address this question as to whether a non-invertible symmetry of this sort is intrinsic or not. One way to phrase it is to ensure that no surface is created in one of these Hanani-Witten transitions. Now, in the bulk, abstractly, a surface is always created. The question whether then becomes what happens to that if we choose a specific global forms and we sort of close the sandwich. It might happen that this surface that is created in the middle actually gives rise to the trivial surface. So there is nothing created at all. If that's the case, it means that the action is actually that of an invertible symmetry, and that would mean that we are dealing with something that it's not intrinsically non-invertible. So we use this as a computational tool to reproduce the known classification of what is intrinsic and what is not for prime rank, for n, and we extend it beyond the case of n equals a prime number. And since I'm running out of time, I'll skip the Argyres-Douglas example, but I'm happy to discuss if you wish, and I'll go to my conclusions. So I wanted to convey the idea that the symmetry TFT is really the organizing principle in the world of generalized global symmetries, because it encodes both the symmetries and the charges, as well as discrete gaugings, anomalies, and all of that. And it emerges actually very naturally, both in geometric engineering and in holography, where in both instances there is a natural notion of radial direction and a clear separation between the dynamics and the kinematics of the symmetry. Operationally, we need to perform a truncation to a topological sector so that we can describe both symmetries and generalized charges. And in practice, Hanani-Witten transitions are great at generating many interesting examples of this. As you can, there are several interesting directions. In a sense, most of the examples I discussed can also be studied directly in field theory very efficiently. But it's natural to ask whether these stringy methods can now be applied to other theories that might be harder to tackle using field theory techniques. Maybe they elude the Lagrangian description, or maybe we have fewer tools available. And also, I wanted, as a motivation, I emphasized the more categorical nature of generalized symmetries, but in a sense, it would be interesting to find stringy origin of truly higher categorical symmetries. That, I think, is a very interesting open problem. And another problem that comes to mind is like, what about symmetry fractionalization or related phenomena? Those most likely also have a brane origin and would be interesting to find it. And even though I didn't discuss it at length, I did mention fusion, and I believe that to also be an interesting avenue for further research. That's it. Thank you. Oh, yes. Sure, absolutely. No, absolutely. So we, yes, we wanted to focus on where is it? Yeah, on a concrete example, even though we believe we can do other things as well. So this is a specific theory engineered in type 2b with its geometry. And here I have included this tau monomial as a marginal coupling. And I've done this because, as it was also emphasized in this recent work, this very same Fourier-Douglas theory can also be realized starting from a CFT in 6D on a T2. And in that duality frame, tau becomes the modular parameter of the T2. So that shows through this dual frame that if we tune tau to very specific values, we can actually construct duality and triality defects in this Argyres-Douglas theories. So what we wanted to try and answer is, can we use branes to understand what's going on in this instance? And so what we realized is, well, first we have to remind ourselves that, with many of these examples, everything has to do with torsional cycles. In this instance, there are 2 cycles. And what we can do is take D3s on these guys. And as usual, we have this binary choice. Either we work at infinity or we wrap the radius. So in one case, we get the symmetries. In one case, we get the charges. But that doesn't answer what the duality triality should be. What seems to be the case based on the dual frame is that when you tune tau to that special value, there is an automorphism of the geometry. And these torsional cycles are permuted according to the action of S or ST. And therefore, it means that there is a geometric realization of this duality triality symmetry. And that would be very interesting to study, but it's a bit harder to do with branes. So what we thought is to instead map this to something we're more familiar with, namely monodrome is induced by 7 branes. But in order to do that, a naked D3 is not enough. You rather have to turn on a word volume flux on the D3. And the effect of that is to induce a PQ string charge inside the D3. If you do that, now, instead of looking at the geometric action that permutes torsional cycles, you can leave the cycles alone and permute the PQ strings. And you can do that using monodromy induced by a 7 brane. So our proposal is that through this strategy, we can bypass the geometric description, which would be interesting to find out nonetheless, and yet get a brane realization of this sort of duality defects in this class of AD theories.
Yeah, I guess general question about the conclusion, but all we know about Brane dynamics is based on supersymmetry, right? And the return effect and so on. While in general, the TFT realized by some topological object, like especially about more complicated fancy higher categories and whatnot. Especially if you want to fusion with many dimensions. I mean, in principle, in terms of Brane, it would break many or all supersymmetries. Any comments on that?
I would say that, it's a very good point. Many of these branes that realize symmetries are manifestly not BPS. As far as the Hanani-Witten transition goes, I do think, however, that it can be argued without relying directly on supersymmetry in various ways that ultimately are tied to the gauge invariance. We can either use this magnetic current point of view, or we can use the original argument that is based on the trivialization of H3 by the gauge field on the brane. So it seems to me that ultimately it really relies on more robust features of the brane. So what kind of degrees of freedom live on them and what kind of gauge symmetries we have. So I do believe it to be robust enough to survive without supersymmetry.
Maybe do you have a concrete example of a theory which has also the anomaly term as a condition?
Well, examples there are many. For instance, in n equals 1 super Yang-Mills, there is a mixed A-B-B anomaly between a zero-form symmetry and a two-form symmetry. And that arises, for instance, by a possible source are these cubic terms. That's a natural origin for these objects, in that all these various fluxes get expanded almost like a KK expansion onto various forms in your link. And the external legs are carried by gauge fields that ultimately become the background fields. So even though the details depend on the setup, the philosophy is that cubic couplings such as this, or the CGG coupling in M theory, it's another example, all of those are a natural source of cubic anomalies. Oh, no, thanks. Yeah, maybe, right. So maybe calling them anomalies is not entirely correct. They are couplings in the SymTFT. The SymTFT is perfectly well defined. It doesn't suffer from gauge anomalies. It's well-defined discrete gauge theory. Once you have these couplings in the bulk, and you choose the topological boundary conditions on the other side, you can sort of close the sandwich or reinterpret the sandwich as an anomaly inflow. So the bulk couplings will imprint an anomaly of your QFT. So it is in this sense that I'm calling them anomalies.
Okay, if there's no further questions, then we can thank Federico again. At 4:10. Yeah. Yes, it's better.